Delcambre. I go by Delcambre pretty much everywhere on the internet. And just before I get started with the actual talk, I kind of wanted to relay a little story. So yesterday, Nick Cox gave a talk about failure and kind of recovering from it. And he told this story about, from Steve Klabnik about a bad rescue release, 1.25.0. And it was me. I was the friend that made the release. If you want to know more about that, I'll tell you about it later. I have opinions on what could make it better, but anyway. So right now I live in San Francisco, but I'm actually from here. I grew up here, went to Portland State. I used to live a couple years ago, just like 3 blocks down, so I'm very much a local to this city and community. Now I work down in San Francisco at GitHub. I work primarily on the back end, so I work on the piece that gets the Git data from the file servers up to the web servers. So anytime you're looking at a repository page and there's like files that come from Git, that's the piece that I work on. So all that said, on to systems programming. So the talk title is Ruby Systems Programming, but the goal isn't really to learn how to write system software in Ruby. It's more about all the system software that sort of underlies all the pieces of the stack that we work on every day. So the goal is sort of knowledge and understanding and comprehension of these lower levels, but not necessarily something that you're going to go and write. So there's not a lot of code in this. There's a little bit at the end, but it's much more about the building blocks and the pieces more than the learning about it. So what do I mean by system software? I took this quote from Wikipedia. I really like it, and it has 2 pieces. I'll read it first. So we're going to operate and control the computer hardware and to provide a platform for running application software. So there's these 2 pieces. So we're both connecting directly with the computer hardware, and there's this piece we're talking about a platform for other software to run on top of. So we're doing very low-level things where we're talking to the hardware, and this is software that usually doesn't have a user interface directly. It's software that other software is running on top of. So we're talking about APIs and interfaces between programs more than user interfaces. Another little piece here, there's that phrase application software. And to me, this means basically all of the software we think of as software every day. This could be web browsers, iOS apps, video games, anything you think of, Keynote. But for the purposes of this talk, because we're all rubyists and we work on the web, when I say application software, I'm talking about web software in this context. So basically what I'm thinking of is basically between the bottom of the Rails app and the top of the hardware. So just from that layer down. So these are the building blocks I'm going to talk about. We're going to start low and work our way up. So all the way at the bottom, we have the kernel that talks to the hardware. We interface with the kernel via system calls. For a lot of the things that we talk about in a UNIX operating system, we're talking about file descriptors. We're going to talk about sockets, how we do web programming or network programming, HTTP for the web, and that gets us all the way basically to the bottom of Rails. So this generally should apply to any Unix-ish operating system, but anything specific you see is pretty much going to run on Linux. So there's a little bit of code here and there, and it's sort of more Linux specific than anything else, but it should apply to anything. It's definitely Unix, though. This is the kind of software that really matters what operating system you're running on. So the lowest level, we're starting at the kernel. This basically controls everything about the system. This is the software that runs, that controls all of the other things, all the other processes that you have. So this is my basic diagram of a computer. This is a computer. Down at the bottom, we have the hardware that everything runs on top of. And then we have 2 sort of different pieces of the computer that we run software in. So we have the kernel, which has a set of responsibilities and permissions and things that it can do, and then your code runs somewhere else that's not the kernel. Your code runs in what we call user mode. So user mode is really restricted as far as what it can do. There's only a couple of things that I think of as it being able to do in user mode. Something I call math, which is basically anything you have where you have 2 things or one thing maybe, and you're doing operations on it locally, but you're not really reaching out anywhere for it. So this could be simple math, addition, subtraction, string concatenation, crypto stuff, crazy things, but it's stuff you have locally that you're just kind of operating on. And the second thing is you can access memory, but only memory that you've already been granted by the kernel. So you can like read and write from the stack and read and write from the heap as long as you've already got the memory local to you. So what's not here? It's sort of everything else, right? You can't talk to the hardware, you can't do networking, you can't read and write files, you can't output sound, you can't talk to a display, you can't output a terminal, you can't do anything, really. There's so much you can't do here. So on the other hand, in the kernel mode, you can basically do anything and everything. There's nothing you can't do in the kernel mode. This can execute any instruction on the CPU. So these modes are actually enforced by the hardware. You can read and write from any memory. You can talk to the hardware. You can write to the screen. You can output sound. All the things that you can't do in user mode are all capable. You can all do them here. So we need to talk between these two layers. We need some way to get from our mode, where our code runs in user mode, down to the kernel so that way we can talk back and forth. The way we do this is called system calls. Get into this a little bit deeper. So here's our computer again. We kind of took the hardware out at the bottom there. You might think that what happens next is that you're basically chugging along in user mode. You need to do something like write a file, which we know we can't do in user mode. So you like switch modes into kernel mode, write a couple of lines of code to write the file, switch back into user mode, continue on your merry way. This is not how this works at all. You do not get to write code that runs in kernel mode. So we have to use this interface, this API that we call system calls, that allows us to talk to the kernel mode. So we have this basically barrier, this API that allows us to ask the kernel nicely to do things on our behalf, like write a file, open a file, talk over the network. But you do not get to write code in kernel mode unless you're writing kernel software, which is a whole different beast. So how do you know what kind of things that your program is doing? How do you see these API calls that we're making? This is on Linux. This is a command line tool that you can use to see what all the syscalls you're making is, called strace. You pass it a process ID, and you can see all the syscalls that happen for that process. I did this locally on a dev environment of the Gist app at GitHub. I recorded it. You can see them all go by. Takes a couple of seconds. So a lot of this is going to be kind of esoteric. There's a lot of things here that we don't really care that much about, sigproc mask and other things like that. But there's some things in there that maybe look familiar. So there's send-to, we have a close, an accept, get parent process ID, get PPID, things like this. So these are things that allow us to do basically everything in the process, in the web request. So in that request, that was actually updating much faster than the frame rate of the video. That one request, 120,000, more than 120,000 syscalls. You might imagine that because we can't do basically anything without the syscalls, and we do 120,000 of them in one request, at least in this case. Could be lower, but you might imagine that there's a lot of syscalls, that this API layer would be really, really huge to allow us to do all of these things. But it's actually really small. So this is the syscall table in Linux. This is from the Linux kernel source. If there's not a syscall in this table, you can't call it. Like Linux won't know how to handle it. This is the full extent of all of the syscalls that you can talk to the kernel about. There's a total of 326 of them. A short aside, this is the actual assembly for how to make a syscall. This is the open syscall. Looks like that at the top. A quick overview of this. I don't know how many of you have seen assembly before, but basically we're just doing a couple of moves into registers and then calling a software interrupt. So open is syscall number 5, which is what we look up in that syscall table, so we don't have to remember that. We put that into EAX, which is where the syscall handler looks for the syscall number. The args go into the subsequent registers. If you have more than about 5, there's a different calling convention, but that rarely happens. Syscalls tend to be a really small API. They have very few parameters. So then we call the software interrupt 80 hex, which is like 130 in decimal. That triggers the CPU to switch modes into kernel mode and call the interrupt handler in the kernel. The kernel interrupt handler looks up the syscall, or the interrupt handler for number 130, 80 in hex, and which happens to be the syscall handler. The syscall handler looks in the AX register, pulls out number 5, looks it up in that table, sees that it's open, executes the code, and returns back to you with the result. So the important part here is that once that interrupt gets called, you are no longer executing your code. You are in the kernel, you are done. Until it hands control back to you, your code is no longer running. So it's really, really asking the kernel to do this thing nicely for you. Another kind of little funny thing about this, this is the syscall table again, and 65 of those syscalls are implemented as the sysni syscall. And that ni stands for not implemented. So of those 326 syscalls, 65 of them don't do anything at all. The rest, there's 261 left, so that's the entirety of all the syscalls that happen. The reason for this is that because of the way that it's implemented in the kernel, we need to know what all the positions are, so there can't be blank spots in that table. So if you deprecate a syscall, you still have to have something in that table to hold the spot. If you want to reserve one for future use, you have to have a blank spot in the table. There's a lot of syscalls that only happen on one architecture or another, so maybe only on x86 and not on, I don't know, Spark or something like that. Again, has to be a blank spot in the table. So 261 actual calls. In Windows, there's supposedly thousands. We don't have this file. We can't cat the or pipe word count on the syscall table in Windows, but people say that there's thousands. There's at least 1,000 or so documented, but no one really knows. And I find it really interesting, like the power of these two APIs is the same, right? There's nothing you can do on Windows. There's no program you can write on Windows that is impossible to write on Linux, at least not at the syscall level. So thousands versus 261. I think that's really cool. I like the smallness of the API. So we have these 261 syscalls that we want to make. There's kind of a consistent way for a lot of things that we talk to these syscalls. We call this file descriptors. Basically, in Linux and in most Unixes, the idiom is everything is a file. Linux doesn't take this completely all the way as far as other operating systems do, but most things are files. There's a couple of things that don't work this way. So files are obviously files, but there's a bunch of other stuff that also is treated as files inside Unix. Pretty much any hardware, printers, sound cards, monitors, terminals, including sockets, that's what we're going to cover next. But all of these things you interact with once you have them via the same API. So you get each of these things. You open one up to talk about it in a different way, but once you have that file descriptor that refers to that device, that file, that socket, whatever, you use it in the same manner. And this is the entirety of the file API that you're going to use on those file descriptors. You can read from them, you can write to them, and you can close them, so you can't get rid of them. lseek's kind of a special one. lseek allows you to move around in a file. So if it's a normal file, like you can read from the beginning or read from the end or things like that, this obviously does not work on things like a sound card or a socket on the network. You can't rewind the internet, unfortunately. So that one still is part of the file API, but it will error if you pass it the wrong kind of socket or the wrong kind of file descriptor. So this is all of the file descriptors that are on one of our Unicorn processes in production at GitHub. There's a couple of interesting things about this. The first is that you see how I'm getting these. This is out of the proc file system on Linux. So I don't know if you know about this, but every single process on Linux has an entry in the proc file system that has a bunch of cool stuff in there, including all of the file descriptors. So this is just a directory of symlinks that point to what all the file descriptors point to, just by number. The second thing is that pretty much every Unix process is going to have at least 3 file descriptors open. Those are 0, 1, and 2. They're at the top there. And those correspond to 0 is standard in, 1 is standard out, and 2 is standard error. These are how you communicate with a program normally, like on the terminal. This is a web process that's running, that's a daemon, so it closes its standard in, it's not receiving input, and the standard out and the standard error in this unicorn go out to the unicorn log. There's a couple of other sort of log files in there. We have a production log from Rails, the pigments log, number 35 over there, for our syntax highlighting things. And then we have some like pipes and things like that probably for inter-process communication, and then a bunch of sockets. We're going to talk more about sockets in a second, but these are generally any sort of network connection that we have open to anything. So this could be an incoming established connection that we're like processing for the web. Could be the socket we're listening on, so that way we can talk, or we can wait and get incoming connections. But it's also like maybe the client connection to MySQL or Redis or Memcache. That's why there's so many of them, because we use these for basically anything that we're talking about over the network. So I keep referring to these sockets without talking about them very much. I'm talking about BSD sockets here. There's a consistent API, but first, just a short bit of history. So back in the 1960s, I think it was around 1963, there was an operating system, a research operating system called Multics that was developed at a big consortium of a bunch of different places, including AT&T Labs, MIT, et cetera. It was very far-reaching and never successful, really. It had some interesting ideas, and they were successfully working on it, but nobody ever used it as a real operating system. It was too ambitious for the time. So a few years later, 2 of the members of that team, Ken Thompson and Dennis Ritchie, still at AT&T Labs, sort of took a step back from the overarching goals of Multics and wanted to scale back the design goals and made a much simpler operating system that they called UNIX. Multics was intended to be multi-user. UNIX was originally intended to be single-user, hence the name. They added multi-user support to UNIX at some point, and they switched it from the CS to the X. That's the history of that name. So due to the antitrust settlements and the baby bells of the 1950s, AT&T was not allowed to sell this operating system without releasing the source code for it. I don't know all the details of this. You can read a lot about it. It seems really complicated when I was looking it up. But the short version is that all of the, anybody who wanted, or I don't know exactly the details, but basically if you were a university and you wanted to get access to the source code for Unix, you could. And a bunch of universities did this, including the University of California, Berkeley, in California. They released in 1978 the first version of BSD Unix, stands for Berkeley Software Distribution. This was a team at Berkeley who released this. One of the men who was primarily responsible for a lot of the porting to new hardware was named Bill Joy, who was sort of famous for two different pieces of software. One you may have heard of, which is C Shell, which nobody ever uses, and the other one is VI, which you probably have heard of. Those were two of the things that were included in BSD, the first version. 5 years later, BSD 4.2 came out, and this was the first operating system that had a TCP/IP stack. This is right when the standardization was happening for TCP/IP. Nowhere really had before that because there was nothing to implement. They were just developing the standard at this time. So they developed an API for how to talk TCP/IP over the network, and that's still the API we use today. And in fact, this is one of the few APIs that actually made it over to Windows, because a few years later, when they wanted to do it, they actually took the same API over there. So 1983, 30 years ago, this API was developed. We're still using it today, and we're basing it on top of technology from 40 years ago. And I think this is really cool. Like, the API is really simple and really powerful. It's kind of a trend here in these low-level programs. This is basically the entirety of the BSD sockets API, at least for the server side. If you're writing a client, this would look a little bit different. But generally, this is kind of the look of it. Go through them each in turn. So the first one creates a socket in the kernel. This is how we create the data structure that we use to talk about these things. This also tells it what kind of socket we want. There's a bunch of different kinds you can use, but generally when we're talking about this, we're talking about TCP/IP sockets. Bind takes that socket and tells it we're going to connect it to a specific interface and port in the kernel. So we're not actually listening on that port yet, but it just binds it to that port in the kernel data structures. Listen takes that socket that's bound to that port and turns it into a listening socket where it's in passive mode and ready for incoming connections, but we're not ready to accept them yet. Accept takes that file descriptor, that same socket, and blocks and waits for new connections to come in, and then once the new connection comes in, it hands us a new file descriptor that we use to talk directly to that client that we were talking to. And the last three, this might look familiar. So what do we have at this point? We have a file descriptor that we can use to refer to that client that we're talking to. So we have read, write, and close. We can read from the client, we can send stuff to the server, or send stuff from the server, write to it, and we can close it, which ends the TCP connection. So all of these things basically establish these low-level APIs, or low-level connections between the client and the server. But once we're to the point of read and write there, all we're doing is bytes. Like none of this stuff cares about what we're sending over this wire. So we need another higher-level API that we can use to talk about these things, or to talk. So again, we're talking about the web here because we're all web programmers, we're all on the Rails. For us, this is HTTP. This is the higher-level API we use. You probably have all seen this before. We're kind of familiar with this. But our quick overview of HTTP. The first line there is really important. That's consistent across every HTTP request. We have the verb that we get. In this case, it's get. Could be put, post, delete, head, info, options, etc. Patch, goes on and on. The second parameter there with white space delimited is the path. So this is everything after the hostname and the URL, basically. If you had params with, foo equals bar or whatever, that would also appear here just in the normal GET request. Then finally, we have the HTTP version. So this is HTTP 1.1. Soon, we're going to have HTTP 2, which operates a little bit differently. I know less about that, so don't ask me questions. And then we have a list of headers. And these are mostly arbitrary. I think pretty much every web server will handle any headers you give it without too much complaint. There's some that are more important than others. This is basically saying that I'm curl coming in from a user agent. The host that I'm going to is Google. That one's important for virtual hosts and things like that. And we're accepting any content type to come back. If this was like a post request and we were sending data along this, there would be one blank new line and then all the data that we're getting after that. The server processes the request, returns a response back. Sort of similar format. We have that first line. It says we're talking HTTP 1.1 again, and then both the numeric and the text version of the status code. This is 200 OK. This could be 404 not found, 500 internal server error, 301 found or whatever. Any one of those, right? Then we have the headers, we have the date, some caching things. It says we're going to get back HTML. Then we have the response body after one blank new line. So again, this data is going to be HTML because that's what content type we're setting on the way back. So we basically made it all the way up to the bottom of the Rails app. Let's look at some code. Oops. So a couple of caveats here. I would recommend not writing this code. Like, we have libraries for this already. This is more as a demonstration. This is definitely not production code. There are huge security vulnerabilities in this. Please do not put this anywhere on the internet so people will run it. Anyway, this is a 23-line HTTP web server using only the Ruby standard library. I'm going to go through each line in turn. First, we require the socket library, so we have everything we can use. We define some constants for later. It might look familiar from the HTTP slides. And then we get into the meat of it. So we create a new socket. This is going to make the socket API call. We're telling it we're going to do a TCP/IP v4 socket. So this is inet and stream. Inet means IP. Stream means TCP. If we were doing UDP, that would be datagram rather than stream. It could also be inet6 for IPv6, and a number of other options as well. But this is kind of the most common. We're going to call bind. So we're passing this data structure that the lower level pieces know how to use. We're basically building it with this little helper. But this says we're going to listen on localhost 127.0.0.1, port 11.0.8.0, which is just arbitrary for me. We call bind with that structure. Then we call listen to put this into this socket into listening mode, so it's ready for incoming connections. The parameter there, 5, is how deep the queue is. So this is how many incoming connections will buffer before we can handle them. So we're going to be processing connections while the accept loop isn't waiting. So if a bunch of connections come in all at once, this says 5 of them basically can back up that we can handle on the next iteration. This is not a good way to do concurrency, by the way, from the talk earlier. It's not concurrency. So then, in a loop, we're going to block on accept and then get this client socket back. This is the file descriptor that we use to talk about the client connection that we're getting. So this will wait until a new client connects and then return, and then give us the thing we can talk across it. Next, we have my high-performance, 100% standards compliant HTTP request parser. If you remember, this is the first line of the HTTP request. So you can see I'm just taking the first line, splitting it on spaces, and taking the second one, which happens to be the path. We take an expand path from the current file directory, the path that we pass in, grab it. Like I said, a couple of security holes, maybe. So if the file exists and is a file, then we're going to return it to the client. So first we read the file off disk. We write out the 200 OK. This is the first line. We write out the content link. The browser gets unhappy if you don't send this, so this is kind of my one header that I'm sending. And then we have those 2 new lines and the contents of the file. And you can see we're calling a write directly on that file descriptor. If, on the other hand, we do not find the file or it's a directory or something like that, we just write the not found, which is the constant. Again, it looks familiar from that previous slide. We're just returning 404 not found with the content length and the string not found. And finally, we close the socket. So there it is, 23 lines of an HTTP server. So just to prove that this actually works, so I have a directory here set up. It's 2 files. There's the server, which is the server that I was just running. And then we just have this one little foo.txt file so we can use it. I'll just put something in there. All right, so let's run the server. Hopefully this works. And then back to the web browser. I was running this on 127. So we're not asking for anything, so obviously there's nothing there, so we get not found. If we pass it foo.txt, we get hello Cascadia. It's working. And obviously, because it's looking for any file that's in the same directory as the server, that includes the server itself. So we can also find Oh no! Oh no! All right, well anyway, it works most of the time. So, yeah, look, it came back. So just to prove that this is stuff that actually gets used in real life, other than my somewhat broken code apparently, I looked inside of Unicorn, and I found the piece that actually creates the IPv6 server. The IPv4 server is a little bit different because it happens in a C library, so it's a little harder to see. But this is the one that creates the IPv6 server. And you can see there's a couple of lines here that look familiar. We create socket.new. This is doing AF inet6 instead of just inet, so we're doing IPv6 with TCP. We call bind with the exact same parameters, called bind with that sockheader-in structure with the port and the address. And then down at the bottom there, we're calling io.select. And io.select is basically doing the same thing that accept was doing, but it means that we can listen on multiple file descriptors at the same time. So Unicorn can listen on multiple interfaces, and if you accept, you can only accept on one of them at a time. So if you're waiting for two connections on two different ports, and one comes in over here and you're listening on this one, it doesn't work. So select basically says, I want to listen across all of these, and it'll return whichever one comes back first. But it functions the same as accept was in our example. So that's basically it. So we started at the bottom, down at the hardware. We have the kernel, which manages all of the hardware and also all the processes that happen on top of it. We need to ask the kernel to do most things for us that talk over the network and a bunch of other things. We do that via system calls. Anything we're talking over in the network looks like a file to Linux, and so we use these file descriptor APIs to talk over the network. Finally, we have sockets on top of that, which allows us to create these web servers, and we talk over those sockets over HTTP. If you're curious about more of this, these are some of the resources that I used for doing this. This is a really good book that I love. It just came out in second edition a couple of months ago. It's Linux System Programming by Robert Love. It goes over basically all of the syscalls that happen down inside of Linux. Robert Love is an awesome kernel developer and a really good writer. This is actually pretty easy to get through. I found myself sort of reading it more when I was trying to look stuff up. It's kind of fun. It's not too long either. It's pretty thin. This is the Bible of Network Programming by Richard Stevens. There are other authors that have been updating it. He passed away quite a while ago, so the versions that he was the sole author on are quite outdated now, but they keep releasing new versions. This is a beast of a book. It's kind of the Bible. It definitely, you can look up references, and I wouldn't really read it cover to cover. And then finally, this is APUE, Advanced Programming in UNIX Environment, also by Richard Stevens. And this is kind of the equivalent of Linux system programming, but for all of Unix. So this covers Solaris and sys5 and BSD and everything else. It's very in-depth. Again, a better reference book, but it is very good. So thanks a lot. I go by Delcambre on the internet. If you want to send me an email about anything, I'm Andy at github.com. And thanks for listening.